So yeah, if you look at that, if you look back at that chart,
1 sec, I'm gonna present screen again. Okay, so all I was saying is when we look at the chart, let's start with the 2D sphere, right? So 2D sphere, you have a sphere, and then when you travel along the sphere, it's doing this. When you collapse a sphere into the one-dimensional, you just get a line. But then when you travel along that proverbial sphere, you just see this movement.
You only see this movement.
Assuming zero means a center.
That's right. Zero would be like where the center of the sphere winds up mapping to. So you can think of it. You can think of it as the mapping where I have to again be careful here with math terminology. Like technically, this is the one-dimensional sphere because it only involves traveling along one line along the sphere. But I'm kind of taking a liberty and saying that just like the one-dimensional triangle is a line segment, is modeled by a line segment. Also, the one-dimensional sphere is modeled by, traversing a line segment, but also there's some kind of a middle point in the middle. So they are not quite the same structure, but you can kind of, if this kind of makes sense, if a sphere, for something to be a sphere, if you have to be able to circulate, then the way you can kind of think of it is that the easiest way to produce a sphere is through discrete methods, is you realize it as a triangle. And for a four-dimensional, for a three-dimensional sphere, you use a tetrahedron. And for a four-dimensional sphere, you use the next, it's called a 5-simplex and a 6-simplex. So it turns out that the idea is that a simplex is actually the simplest discrete realization of the sphere. The sphere is a property of an object that has a certain property of being able to go somewhere and come back. Whereas the triangle is defined by a different property, but they happen to be the same object when they're zero-dimensional, when they're one-dimensional. But of course, when they're two-dimensional, they start to behave very differently. The two-dimensional sphere or the circle, really that's in technical terms the one-dimensional sphere. Some topologist will watch this and be like, that's a one sphere. And I'm like, yes, I know. But I'm trying to simplify this as, right, if you see a sphere on two-dimensional paper, you call that a two-dimensional sphere. Most people think of a ball as a three-dimensional sphere. Mathematicians call the three-dimensional sphere the three-dimensional space that covers the four-dimensional ball. And that's not the way you and I use that terminology of sphere. That's a very terrible naming convention that mathematicians have adopted, but so be it.
So I know we're moving in a direction that the opposite direction of where I want to go, but just because you wrote it down there, fourth dimension, it's a hypercube tesseract. And so if the fourth dimension, let's say we assign as time, then it'll be like interstellar, where you basically have a fixed point in space and then just different time. Then they can travel along those different times. But then in this case, a fourth dimensional tetrahedron or a triangle versus a fourth dimensional sphere, are there actually, how do they differ?
They're very different because here's the idea, and this is actually where we talk about the idea of simulation. Oh, I'm sorry, wrong marker. When we look at the idea of a simulation, when we describe a simulation, there has to be a space, there has to be object states in a simulation, and then there has to be transitions between the states. And it turns out that these transitions are what essentially mark the time in the space, whereas this marks what we would typically describe as space. When we describe objects or locations in space, we're really saying that there are states, Christmas ornaments hanging in space, X, Y, and Z Cartesian coordinates, just like little Christmas ornaments hanging in space. Every point has a coordinate hanging there, telling you what it is. So space is to state as transitions are to time. Now, this is important in 4-dimensional, what you'd call space-time, where you treat time as a spatial variable, that's in the Einsteinian mix-up, or right? The problem with describing them all as spatial states, the intuitive problem, not they have a rigorous method for how they disambiguate it. That's obvious once you study it for a while, because you see that the speed of light squared is always in the time factors and they're not in the spatial factors. But that's just a technical point. But the thing I'm trying to explain is that if you decide that I'm going to draw first off a 4-dimensional tetrahedron. So first, what we do is we build up. We take a 2-dimensional triangle or a 3-sided triangle, and we just take a point that's outside of it, and we connect each new point to that point. Now, this is a terribly drawn tetrahedron, but this is a tetrahedron.
Yeah, but I get your point.
Yeah, this is a tetrahedron.
But there's an invisible edge going from the top point to the bottom point.
It's an invisible face. So the edge that goes from top to bottom is in fact this edge.
Oh, the circular one. Okay.
That's right. The circular one is that poorly drawn edge that would be normally like this.
Right.
Except that this now draws the faces clearly. This is a face.
Correct.
This is a face. This is a face, but then the negative of the image behind the image. In other words, you can imagine them sitting on the ground like a tetrahedron looking up at you. These are really just, those 3 faces are 3 triangles pointing up at you. So the backside is also a face. So there's 4 faces, 1 invisible, 3 visible, in this particular drawing of the tetrahedron. Now, if I want to go from triangle 3 to triangle 4, I just take a point that's outside of it. So I'm going to just draw it again. And my students will be like, that's a bad drawing. And I'm like, it's intentionally bad. I'm intentionally helping you get used to a tetrahedron in graph theory, not looking like a geometric tetrahedron.
Because we're projecting, what you did on the left there, you projected a 3-dimensional object onto a 2-dimensional space.
Now what we're going to do is we're going to take a new point, and now every old point gains a way somehow of getting to that new point where they all don't intersect, right? They all just go.
Right. Of course, that's impossible to do on the 2D space. That's
right. So now this is now our 5-dimensional triangle. A triangle that exists in 5 dimensions is triangle to the 4th power, or the 4 simplex. So this is a 4 simplex.
Oh wait, hold on.
Sorry, 4-dimensional. 4-dimensional.
Yeah, I was going to say 4-dimensional. That's not 5-dimensional.
5 points. 5 points. 4 dimensions. Yes. Sorry about that. So yeah, and of course the exponent is the dimension, and also exponents are logarithms, and logarithms are dimension conversions. So so that's a whole nother thing, but they're basically the same thing. So this now right here, here's the problem. This thing, how many tetrahedrons are in this object? Well, it turns out that there's 1 tetrahedron, 1, 2, 3, 4 for each new point that we add in. Just like there's an original tetrahedron, which is the 5th one. In other words, just like there's 4 triangles that make up this guy is made up of 5 triangles, or 5 tetrahedrons. Sorry. Oh, I'm so sorry. That was the wrong thing. Okay. No, I'm sorry. I counted wrong. It's not 5. There's 4 of them. 1 for each new point.
Let me think. Going back to the 3D one.
In the 3D case, there's 3 triangles.
No, there's 4 triangles. There are 4 triangles. The tetrahedron has to have 4 triangles.
You are right. Thank you for that catch. I appreciate that a lot.
Right, so every time you add a dimension in 3D, you add a point, and you have to form 3 new faces. So altogether, you have 4 triangles. And
Yeah,
then going from 3D tetrahedron to 4D simplex, you add a 5th point and created 4 more. Yes, so yeah, they're total of 5 tetrahedrons.
that's right. Oh, sorry, I did this wrong. The reason I got fooled is because when I was taking the figuring out how many of the smaller type triangles fit into the bigger type triangles, a calculus formula flashed through my head, which is the basic derivative, which is called the power rule, right? So if you have triangle to the nth power, how many smaller triangles would there be? And if you use the power rule, it would be n times triangle to the n minus 1 power. That's just like, x to the 4th. When you take a derivative of it, it's 4x to the 3rd.
Oh, yeah. Yeah.
That's a calculus derivative. I was thinking that it's the same thing, but it turns out it's this plus 1. So that's why there's 4 of them.
Plus original.
In other words, it's not n, it's n plus 1. So it's actually, if this makes sense, it's like a derivative, but it's offset by 1 from the original.
Like derivative, but offset by 1.
Yeah. So instead of it becoming n times n to the n minus 1, it becomes 1 plus n times n to the n minus 1. So this would be the this is
the way I think about it is just the plus 1 is the one, the original one that you have to include.
exactly. And what happens is, why I got it wrong? Can I tell you that you'll love this? What kind of derivative, is for Curt, what kind of derivative is this derivative? It's a derivative in continuous space. What kind of derivative is this derivative? It's a derivative of discrete space. What's the difference? In the discrete space, you have to add 1 because you actually have an original unit to count for. Whereas in continuous space, when you're dealing with squares, so in continuous space, all the math that we're doing with triangles, let me do right now, real quick. Let's just say you have a cube in continuous space.
Yeah.
So this is square to the 3rd power, basically, right? The derivative would be 3 times that squared, 3 times, square squared, because that's indicating that when you increase in size, you're adding to this square, you're adding to that surface, and you're adding to this surface. In other words, whenever you do a tiny little increase, which we'll call d square, d stands for a tiny increment of the shape of a square. If we increment our shape upward, we add a coat of paint, we have to add basically 3 surfaces worth of paint to the cube to make the cube keep getting bigger. So that's where the derivative, this is what the derivative calculates in geometry, in continuous geometry. It calculates the surface of, it calculates the volume of the surface of increase. It's the marginal cost, basically, of expansion. The derivative calculates the marginal cost of expansion, and the integral adds up those incrementally small costs of expansion into one solid shape. But of course, points have no size, you see, in continuous space, and so you don't actually add a point. In other words, let me just explain this. If I wrote this plus a point, the point is 0, so you wouldn't even think to put that in the formula. You would just say that it's 3x squared. That x squared, you would take a derivative of it, and that just becomes x squared. We don't think to write 3x squared. We don't think to write 3x squared plus 0, where 0 stands for that size of the point that the original object came from. We don't think to do that. But in the discrete space, you correctly pointed out that we do have to count the original object. So it turns out that the formula for the derivative in the discrete space has a slightly different power rule, but we just derived it. And you proved to me why I was overlooking it. And then I realized, oh wow, I'm lost in the math of continuous space, which is the odd one out.
So
right?
Originally, we went down this route to figure out what a
transitions.
Actually, what a four-seam sphere will look like. So this is a four-seam tetrahedron.
Let me explain something really important, which gets to the root of that, which is that there are 5 different tetrahedrons here. You would have to claim that for each tetrahedron, in other words, there's 5 tetrahedrons, and then there's correspondingly 5 timelines. In other words, you would say that the timeline shows the evolution of one tetrahedron into. In other words, if you're claiming that one dimension is time, then that means that a tetrahedron is going to evolve into a different tetrahedron. Okay?
No, it's actually, I see. By adding that dimension of time, there's
you have to prove that. Yeah, you have to prove that every single possible one of these 5 lines is equivalent to a timeline. In other words, they could each serve as a timeline while the other was an evolution of space. And the problem is with most people's movie camera concept is that if you're not working with as simple of an object as a simplex or a 3-dimensional triangle, 4-dimensional triangle, or 2-dimensional sphere, 3-dimensional sphere, what winds up happening is that each particular line to the next dimensional point, those 5 different turquoise lines that I drew, right, to create the 4 simplex, each of those lines for a more complex shape is not going to behave well as a timeline for the other shape evolving. Only when all the shapes are triangles does each timeline behave equally well with the other corresponding triangle. So we can, in other words, only with triangles can we exchange space and time and space. And the same is true in the continuous space for squares, but that's Einstein math. But in the discrete space, this works with triangles. However, if you get in the habit of thinking of the 4th dimension as time too much, then how do you go to 5 dimensions? How do you go to 6 dimensions? Then you have time of time, time of time of time, animations of animations of animations. It's better just to think of it as.
Well, let's use some other dimension. Let's say temperature, right? I got 3D, I got a 1D4, which is tetrahedron, and then 4th dimension being temperature. Then how does this change? Using that analogy.
Ultimately, I wouldn't be able to visualize the temperature changes, but what you're doing with temperature is you're saying that there exists a linear line, which we call the temperature axis, and that somehow in traveling from temperature 1 to temperature 2, we had, molecular state 1 and then molecular state 2. And this would be the picture, right, that evolves. And this would essentially be the time axis. So in the case of temperature is something that if it's going to increase, it's going to increase in time. We don't ever see.
Okay.
Yeah.
Bad example.
Well, it's not a bad example. What I'm trying to kind of show is that the most general form of a higher dimensional shape is to draw it as one of these things, a graph, where every time you go to the next degree of triangle. So here's the 1 triangle. Oh, sorry, here's the 0 triangle. Then to create the 1 triangle, the formula is you take the 0 triangle, and then it's always the same construction. You add a point to it and draw a connecting line. Then to go for the 2 triangle, you have the 1 triangle, and then for that 2 triangle, you draw a new point and you draw corresponding connecting lines. And so this process, it turns out, as a computational model of your higher dimensional space, will never fail you, because every time you construct the next dimension, I'll do it on the inside here. That's a clever way to do it. And that's kind of, you're looking from overhead. But then, of course, in the 4D case, you take
you're not going to be able to project it on the planar surface without crossing without
Exactly. Exactly. But it's simply a representation, and 5D would be that thing with another point added, and so it just gets messier. But that is more of like a file architecture. So you're really describing just states, and it's like a category. You're describing states and you're describing morphisms between states, except it's not a category unless it has the specific properties of what's called a category. But here we're just saying there are states and there are functions between states. So I try to get us out of the time versus space way of
I got it.
visualizing. Yeah, that makes sense. Okay, so then if we take this, just making sure, and we go back to um, simulation, the concept of simulation. Okay, then this will now land us squarely in um, the game world. Okay, so
Which one of these whiteboards are you on?
oh,
Number 17 or 16?
15 billion. No, let me see. Let's actually go back to the one
The
that
set
is
simulation?
9. Can you go back to 9 where it says and XOR and true and
Yeah,
false are
yeah.
same and distinct?
I'm there.
So what I'm trying to show in my grand project is that this -1 and -2 dimensional levels in this chart are consistent objects all the way up the chart at some point. It stabilizes. So I think in the case of the continuous as well as the discrete geometry, it's empty space. So the -1 dimensional space is empty space. But what's the -2 dimensional space? Empty
Same
space. Yeah. What's a -8 dimensional sphere? Empty space. So now we have a consistent meaning to empty space in terms of dimensionality. Only dimensions -1 and higher make sense as background, to index our background to our objects in the foreground.
I think you're onto something, and I may be wrong, but I think of as moving from, let's just look at a continuous space and discrete space, right? When you get to -1 dimension, they're essentially equivalent. They're both empty space. But then when you move from -1 to 0, you're actually, and then from 0 to 1, you're actually operating. When you move up those dimensions, well, in this chart is down, but when you increase dimensions, you're actually operating on a set of first principles.
Yes.
Operating based on a set of first principles, and those first principles transitioning from dimension to dimension does not change. They may be different first principles between the columns, but they're still first principles. Just which is why, like under category, when we get to negative, category is a little special in that it actually has a -2 dimension, which is you get to true.
You get to identity.
Right.
Which is the essence of category, is there's some identification occurring that we're trying to categorize.
Right.
So it was they sort of named it by accident, but it was a very apt name. Mathematics is usually plagued by terrible naming conventions, but a category is a wonderful name because it's the same as a type. What's a category? It's a type. What's a type? Well, it's like a category. Yeah. And then we get to logic states in a category. Now, what if we, instead of I'm gonna go to slide number. Please go to slide number 4. You've been very patient with me as I run you through these slides. One idea of fixing logic from a mathematical perspective that I'm exploring is we change Venn diagrams such that we look at them like the Mandelbrot set, where the boundary state between true and false, interior and exterior, is itself not a truth value that's either true nor false. It's a boundary case that requires more zooming in or more context needed. So we're just admitting that our simulation, this is the back to simulation now, our simulation of what the thing is too coarse, is just too coarse to operate. Then, if we look at another way of looking at logic, is we say, if we go back to now the chart that I showed you, that's not on screen, but it is.
Oh, it is on screen in the recording. I have a
perfect. Oh, you have a side by side. Amazing. Thank you. Of course you've solved that problem already. So now if you go back to the category chart, thank you for that. If you go back to the category chart now, another way of putting it is that there's three states in the -1 category because there's three possible morphisms, not two, right? So in other words, if you look at a pair of objects in a set, you can say they're the same, which is true. They're clearly distinct, which is false, or we can't tell yet, which would be question
Which,
mark.
by the way, is missing in your chart. So in the chart, there's only true, isomorphic, false, distinct. So there's a third state, which is undecidable. Need more
well, because this is a math chart, I didn't want to put that third state in the natural law chart. So this is only in the Boolean math world that there's true and false. If you introduce that third state of undecidable, everything above that, the -2 category, it doesn't even exist. In other words, the notion of categories may not even survive if you now have an undecidable.
I see. So
it might survive.
It's not,
but
then it's not a
above my pay grade.
category. It's
above
not
my
a
pay grade.
category. It's really I think we need to call it by a different thing.
Yeah.
We need a new column. It may not even be the games column, but it's some column.
Something else.
Just not categories.
Yeah, when you have a ternary logic, you can't really. But what you can do is you can represent a ternary logic as, right? If you do the Hamset comparison, I'm now going to go to slide number 17. If you have the Hamset of, let's just say x with itself, or x with y, doesn't really matter, right? It returns the value of true if there's a path between them. It returns the value of false if there's no heat, there's no transfer between them. But then question mark, right, would be like the other. And what we're really saying is that the answer is independent of the information given. There's something, there's the existence of the transition between them maybe does exist, but it exists because you can leave X to go here in some other system and then go there and then go there and then go here. And then from there, there's a way to get to Y, but but in other words, it's in a different category. It exists in a bigger category than the category that we're studying. So that's how category theorists deal with it, which is they say, if we don't have a path from X to Y in the category that we're in, we create what's called a pre-sheaf. I think this is terminology heavy. And what a pre-sheaf is it's basically a bigger category than the object, than the one that X and Y are in, where X and Y are like sub-objects in that category. And in that new
seems to be a convenience cheat.
Well, that's the idea, is that they keep track of how many layers of cheat there are. And what they show is that a lot of math theorems over the centuries are actually statements in symbolic notation of like X plus Y equals this and that. But they show that in terms of an arrow diagram, that the equation existing is one example of a particular functor between categories. So it's I don't want to get into that, but it's just the idea is that a lot of theorems and a lot of systems in math, in what we would call traditional mathematics, are the decategorified version. So like addition, 2 plus 3 is 5. This symbolic notation is the uncategorified or decategorified version. And as a category, what we're really saying is that there's an operation on, this would be the category of additive groups. And in additive groups, we'd have to look at the morphisms. So, you'd have to show that there's plus 2 is like the function f, and, plus 3 is like, the function g, and plus 5. And then you'd have to kind of prove, right, that like the composition is that plus 5 can only be the unique composition of plus 2 and plus 3 on that tetrahedron. And if essentially you make that proof and you show that that there's really only 3 sides to this tetrahedron that are unique, and the others are just compositions of those unique things. You kind of factored it into prime numbers. You found the prime functions, basically, of addition. where multiplication is the same as composition or associativity of functions. So this is a very complicated picture to teach a child addition, isn't it? So children, remember, something
it
is
actually shows them where addition comes from, why
yes,
addition actually works.
that's the key, is that this is the flow chart or the category but a flow chart is a graph theory picture of the operations. So when we convert this beautiful picture of operations into instead a very simple 2 plus 3 is 5.
Right.
Two stones.
Represented in symbolic language. In
That's right.
fact, it seems like what math is really doing is it takes something that's like moving from the right hand side. I'm looking at the table, right?
Mm-hmm.
It takes something that's from the right hand side and move it down toward the left, and eventually in continuous space represented using a symbolic language.
Mm-hmm. Yep.
It's convenient, but of course it does not describe reality.
It is again, I would describe it as this: forgets and keeps. Something is forgotten every time you convert it to a number because you've numbered it out. Something is forgotten every time you convert it to a graph theoretical picture, because any messiness between the states is kind of ignored. Any friction, any loss of information is ignored unless you draw a new diagram and a crazy complicated flowchart to account for every possible error in every possible situation and every possible state. And that sort of resembles what you deal with at your work, I'm sure, where you work on a sub part of the space station, and the space station has a million of these arrows on the flowchart. Like, if this doesn't work, then this doesn't work. This doesn't work, then fix this. If this is overflow rather here, then might force this not to work, and so forth. Check back to this, but not this, unless this. And it's all arrows.
I think then we're finally getting to the reason why we'll have this conversation, right? The far right column, when we'll have the games.
That's right. That's right. I'm so happy you made that instinct, is because I believe the games are the furthest rightmost thing, because a game is a graph, but it's also a simulation. So what a game is, a simulation is just an algorithm where the states, and then there's the functions that are transitions between the states.
It's a finite state automata.
It's a finite state automata, and you can see in my columns that I put that a zero-dimensional game is basically defined as a game that is isomorphic to, meaning that as a category theory, the arrows work the same way as Conway's game of life, in that there is a winning condition, which is actually, this is kind of interesting, the winning condition. I'm going to go to slide 18 now. So in the zero game, which is the Conway's game of life, I'll just write GOL like that, okay? You make a whole bunch of like square tiles and whatnot, and essentially you get like for instance, when you do this group right here, it creates like a state where then you get like an X, and then that X collapses back into the original state. And so this is a loop, or it's in Conway's terminology, it's actually known as a loopy game. So this is just a game of two states, and there might be games of 3 states or 5 states. Doesn't matter.
And I'm pretty sure it's I've done it a long time ago. I can't remember now, but I'm pretty sure programmatically it's done through a while loop. It doesn't really end.
That's right. That's right.
Well, unless you tweak some parameter and you basically end up with nothing on the screen, right? In which case, I guess in effect it ends.
The question of game of life is, what do you win in the game for? Like, do you win the game when it's funny, it's like, I would say the game wins if it goes on forever, and the game loses, and I believe this corresponds with Curt's truth tables of certainty, because you can show by playing out a dead game, a game will either die, so you have the dead games, and those are equivalent to the truth value of false. And we have evidence of these games being false because we've seen them terminate. False is, of course, equivalent to 0. It's like timesing by 0. No, if you add, and also adding 0 to itself produces 0. Adding a bunch of dead games on the board to one another might just produce dead games, unless the games travel like gliders. Maybe they intersect and create aliveness.
By definition of a dead game, do you mean a finite state automata where there's no way for you to keep on looping and keep on having continue? In essence, it's a directed acyclic graph. You always end up in terminal state.
That's right.
Whereas if the goal of the game of life is to continue playing, which is the point of life in any case, then in this FSA, in finite state automata, FSA, there exists a loop that does not get you into that. If you made the right choice and it does not get you into the end state.
Yeah, I would say so. The loops, the loops basically, you could argue that they're alive because they have energy, so they have an energy cycle. In other words, there's something called a glider, which I forget how to construct it, but it looks kind of like, again, this is like one of those things where like some nerd really knows how to make this, but it kind of it's this like thing that after 3 or 4 states, it kind of moves in a diagonal line. And what people have figured out how to do is to create thousands of these gliders interacting in like crazy and crazier and crazier, bigger cellular automatas, and they never terminate. These cellular automatas never appear to terminate. However, of course, the question is, do you run out of space on the game board? So you might decide the conditions of the game of life. How big is your game board? These considerations are what I consider to be the background of the game, or the negative one-dimensional space of the game.
And that's the rules.
The rules, the logic, the possible allowable game state values, absent pieces on the board, absent any particular arrangement of the pieces on the board. So the arrangement of the pieces on the board is kind of the equivalent of a 0 category. It's a set. It's just a collection of objects, except in a game, those objects evolve of their own accord, absent the intervention of an agent. So a one-player game now has the ability to change, to water the plants in the game of life.
Yeah.
And a 2-player game, and so on. And then you either develop what are called apocalyptic games. Well, I don't know if that's the terminology for it, but I distinguish between apocalyptic games are games in which you can murder someone. You can deal them a 0 game. The idea is that when they have no more moves, they lose. So there are apocalyptic games.
Where does in this table, where does apocalyptic games belong?
I didn't categorize the different types of games. There's actually many different categories of games, but the general idea that unifies these different types of games is that there are multiple players in the game. In the case, there are going to be certain 2-player games where the game never terminates. This is really a dumb game, but imagine that like Francis has an infinite number of cherries and Michael has double infinity number of cherries, meaning that every time we examine Francis's set of cherries and Michael's set of cherries, we always see that Michael's cherries are at a density of 2 to 1 of Francis's cherries, no matter how we make any kind of set theory comparison.
Well, I mean, the infinite game is kind of like one. Infinite 2-player game is kind of like one where you're playing chess, but you can always put the pieces back on the board.
There you go. There you go. There's including a king, and so that's a great example actually. So that would be an unending game. So there's no apocalypse. There's no unveiling of a checkmate on the board. But the apocalypse is the unveiling in Greek. And so the question is, something becomes apocalyptic when you can murder someone else, essentially. Like once you have the power to terminate someone else's, this is back to Kaczynski too, once you have the ability to interrupt someone else's agency or power process or the ability to affect a game outcome to a desired end state, you're dealing them as 0 as from a game theoretic perspective. 0 is the game in which neither side has a move. But when I say dealing someone a 0, I'm basically saying you give them a situation where they have no moves. You might have moves.
Hold on, but does that mean apocalyptic game is one where an agent, a player, can degrade the game from whatever 3-player or 2-player down to the next level. Like, for
I never thought
example,
of
you
that,
could be at
but
the
I think that's
volley, but a
correct.
Puck League game, you could kick out a player and turn it back into a solitaire.
Well, maybe that's what really is the way to think of it. Like maybe in chess, when you checkmate the opponent, even though that's a much more complex game with many if-then conditions,
Mm-hmm.
like there's a 50-move rule in chess.
You could, in fact, keep on playing just by moving the pieces on the board.
I think that's what it is. I think that in the game of chess, it's meant to simulate two medieval kingdoms fighting one another, where they both have perfect loyalty. Whereas in the game of Go, which is where this game theory was actually invented by Conway when he was studying the game of Go, he came up with the idea of, he and Berlekamp and another guy named Richard Guy, when they invented combinatorial game theory, they came up with the idea of sums of games because they saw that on a board of Go.
Yeah.
Eventually, the game becomes 4 separate theaters. There's a corner over here
Correct.
of, and you have no more room to surround your opponent. And so the idea is that since you can only move in one game or the other, and that's a XOR operator, by the way, you can move in game 1, or game 2. And if that's the case, if you can only choose one game in which to place a tile, then that is equivalent to saying that we are looking at the sum of the game position, game 1 and game 2. So from a logical standpoint, again, we see that the XOR operator corresponds to the operation of addition, which only makes sense if you have distinction. Thus, its inverse operation is how distinct are the objects. Versus the and, right? If you have a product of 2 games, that is a hella complicated proposition now. When you say that you have a game's worth of games, in other words, I have this chess position's worth of this many other chess positions. That, like, what does it even mean? It only makes sense from a graph theory or an algorithm perspective. It's basically saying, in this position, right?
Well, it basically means that every time you make a move on a chessboard, you're going to have to play a different chess game.
Yes. So now what you have is you have a structure where you do.
Actually, hold on. Sorry. Using a simpler example, right? Let's say that you're moving a pawn. Whether you move the pawn let's just say the initial game. Whether you move the pawn 2 spaces forward, or that's a bad example.
No, it could be a good example.
Use a knight, right? Use a knight. Knight has how many positions they can go? 6 or something? That if we're saying, well, instead of you as a player chooses which position knight goes, you roll a 1d6. That's the equivalence of that game you were talking about.
Yeah, because if, for instance, this would be the way to think of it. If moving to d6 created a completely different branch of games that had no bearing or interconnected or transpositions between the games where you go d5, and they're just 2 completely separate branches separated by an XOR logic gate, basically, you're now choosing the game of d6 future states or d5 future states, and there's no way that you could ever possibly get back to one of those d5 states if you choose d6 and vice versa. That's XOR. So that would be, you basically are choosing, you're now playing the sum of 2 chess games. You can choose the d5 game or the d6 game. But let's suppose that after choosing d5 or d6, there's all these different ways that the paths branch back, where a move in the d6 game actually can now affect a future state of a d5 game because there's ways in which they can branch backwards. That's where the and operator confuses, you ready for this? Confuses the distinctions between the various games. So what I'm arguing is that confusion, or and, is the basis of the equal sign, and disconfusion or disambiguation, or XOR, is the basis of the not equal sign. And that this is what mathematicians mean when they say true and false. But there is no true and false. They're just describing identity and non-identity.
Right. Identity and non-identity isn't the same as true and false.
Yeah, distinction and confusion is and when you have a third state of logic, the way I teach it to my students is that when you add undecided in math, we say that false. We say that negative false in math is allowed to be true. This is how a proof by contradiction works. But In the real world, negative false is not equal to true. Flying an airplane with 3 wings always crashes. Well, then flying an airplane without 3 wings will never crash.
Right. Right.
It's like, I mean, I kind of abused the logic there, but
yeah, I know what you mean.
But in math, that works all the time. We've now proven that a not thing.
Well, using that airplane analogy, right? Let's say true is confused with flying, and false is confused with crashing.
Yeah,
And not crashing does not necessarily confuse with flying.
that's a great point. Yeah. So in the Venn diagram situation, if you have a Venn diagram of crash and you have a Venn diagram of flying, how do we? It's maybe even impossible to draw this. I'm not sure. I won't try. I won't try
It's Venn diagrams. That's correct, right? So you have one Venn diagram that's crashing, one that's flying, but then just because you're not in either does not mean that you can't be a dot that's outside either circle.
Yeah. See, in traditional set theory, when you choose the set of not crash, that shades in. Oh, I'm sorry. Let me undo that. I apologize. The set not crash, by definition in a Venn diagram, means we shade in all of the not crash space.
Mm-hmm.
So that does include the flying space. However, in the ternary logic, I'm arguing that boundaries are themselves
A state
that requires their own logic test. So then the fill-in would be like this, but it would not penetrate into flying. Flying gets its own criteria.
Yeah.
So the bubbles are actually set that the boundary of a Venn diagram defends the inside of its properties in the same way that the membrane of a cell defends the internal energy state of the goo and whatever inside the cell, the proteins and the goo and all the structures inside the cell. That instead of membership based, it's defense based or something like that, persistence based.
Mm-hmm.
So falsification based. It's all the same thing. So in regards to games, sorry, I don't tell me to stop or slow down if I'm going too
I understand
fast.
where you're going at. Yeah.
So I'm going now to slide 19, and this might be like in golf terms, the 19th hole. It might be what clinches it now in terms of what is a negative one-dimensional game. So just as a negative one, oh, I'm sorry. Let me do the nice drawing. So just
Yeah, you just gotta click on a pen icon and switch to a pen or something. Yeah, there we go.
So just as a negative one category, which we said is the Hom set of a pair of objects in a set, which again is a 0 category. So they mean the same thing. So basically, we either have a pair, which we call true, and then we don't have a pair. We call that false.
Mm-hmm.
Well, now when you look at games, the equivalent of a set is where we have a position, which in game theory, unfortunately, well, maybe not unfortunately, they call it a game. When they call a game of chess, they're actually referring to a specific chess position. So just like in your example, if you choose d5 versus d6, you're choosing 2 different games, and therefore 2 different game positions.
Mm-hmm.
And so I'm saying that that's basically equivalent to a set plus game rules.
Mm-hmm.
So what are the rules of sets? Well, the rules of sets is just that there has to be something called membership. So I'm arguing that membership is what really the one category is about. You have a member or you don't have a member. So in the case of a negative one game, right, it's like you have rules you don't have rules. And so essentially, how many different states are there between having rules and not having rules? Well, I think it's much wider than just true versus false, because here we're really describing that a game itself survives, not the player that survives in the game. Does the game survive? Does a particular game of life, when you run it after 1,000 frames, it dies? Does this particular game persist? So we have survives as the true state, if you will, which again, epistemologically is just possibly true because you have to run the simulation to find out. You can't calculate your way to the end.
Hold on one sec.
Yeah, sure.
Because a so where I think of have rules versus not have rules is have rules means that your game can actually operate.
Exactly.
Right?
It survives.
It does not guarantee survival. Survival is a precondition. I mean, have rules is a precondition to survival, because even without rules, you don't even have a game without rules. You don't even have survival versus non-survival.
Mm-hmm.
A game without rules is anything that goes. You don't know whether it's going to die or whatnot. So I think what I'm saying is have rules versus not have rules.
I think you're right. The rules of operation are really what are meant by the word logic in the negative one-dimensional game. It's right. You have rules of operation. You don't have a game position to run those rules,
right.
but you have the rules, and that is not a question of survival.
Using a chess example, right? Rules of operation means knight can only go this way and queens can only go this way and so forth. But without the position of neither one of those pieces, which is we don't even have a board, you don't have game position, and therefore you just have a knight, right? It's like if you buy a chess set, comes in a box, you take out the instruction, you throw away the board and all the pieces, all you leave is the instruction. That's your -1. It just describes how it operates. But that's different from saying, hey, we got another game of chess that the pieces all look different, board all looks different. There are no rule books. The absence of a rule book is one where it does not have a rule. But that doesn't mean that if you take that no rules game and then you move to a 1-player or 2-player, that just because there are no rules doesn't mean the players are going to die, nor does it mean they're going to live. It's undefined, because you can't even define what live or die means.
This is great.
And then maybe if we apply ternary logic, then maybe there's a third state called I cannot discern the rules. The rules are non-discernible.
Yeah, non-discernible rules. Meaning that we have an existence of game states and we have transitions between the game states, but we have ambiguous rules.
Correct, or rules that always change. Or maybe that's a better example in that have rules means that the rules are rule of law, they're written down. No rules, anarchy. No rule of law. And then there's rule by man, which is you have
rules always change,
but they change all the time. Which means that every case is essentially non-decidable because the rules keeps on changing.
Which one is entropy, or both entropy? Is rule by man entropy as well as no rules entropy? Or
let's play a game elimination, right? Have rules, that's orderly, so it's low entropy. Don't have rules, I would think that means max entropy. No, that's not right. If you don't have rules.
To make it a game, there's one thing that I do have to explain, and then continue this thought branch, please. There has to be some kind of either winning or losing condition for it to be a game.
Right.
Which is, at what point does a particular program or players running up their own program terminate? And then other than that, you have programs and agents interacting with one another. And so following through on your idea, if you have no rules to the game, you actually, I think that's an example of the tautologically false. You can't actually have a game without rules because
But you,
because well, because let's suppose you have a set of states that you see transitioning from one to another. Eventually, you would just name those state transitions and say those are the rules. And there might be a set of like 40 trillion rules. Ultimately, you'd hit some maximum number of possible state transitions.
Well,
I mean,
yeah, so when we go to -1, right? No rules means no state transitions.
so that's a false. That's like the false version of
Right.
category theory. Whereas true would be like there are some form.
Right.
There's some set of rules. We don't know if the game survived or not, but there's rules to the game. That's interesting. So at each level, actually, there's a true false. In the zero player games, there's the ones surviving, the ones that don't survive. And in the one player games, there's you survive or you don't survive. You solve the solitaire game without running out of cards, or you solve the Minesweeper game without getting blown up, or you get blown up. The two-player game, each player gets to pick a different tile on the Minesweeper board and limit your squares. Three-player game, it goes in a cycle
Yeah,
somehow.
I think it comes to I think if you think of it this way, right? When you're in the cell, what is it, -1 game, where we're just describing the rules. Only the games that have rules can actually operate and can go to games of zero dimension, an algorithm, and therefore further go on to games of one dimension, single player, and so on. Because even if you have no rules, i.e., no state transitions, you can't have a game. It's not what we think of as game. It may be something else, but it's not a game.
It's a trivial game. It's like
even dies is a state in that transition. Is a state in that FSA, right? Without rules, you can't die, nor can you live, and it's just undefined.
That's right. That's right.
Then let's test my third thing. So have rules, don't have rules, non-determined, or what would be the ternary logic? Undecided.
Yeah.
Maybe undecided is just you. Well, I can only think of this in the game sense that for example, it's a algorithm, and you can
No, you have it.
see the
This is it.
state, but you do not know the state transition. You have not
That's
figured out
it's the game we're in. It's the game we're in with natural law. You have to actually, when it's undecided, you have to pay a price to find out what the rules are. You have to interact enough with the game and have enough of your own memory to start figuring out and deciding what the laws are.
Well, that is a game of life. I mean, not the Conway's game of life, but the very
real
game of life, the EC that we're engaging in, is the gradual discovery of these rules.
So I think your thing holds. I think your idea does hold. This would be a non-game if there's no rules. This would be a simple game that we just call a game. And this is not the Conway game of life, but this is, in fact, I don't want to even say the game of life. I'll just say
It's called
real.
EC.
Oh yeah, EC, evolutionary computation. Real life.
In real life, in evolutionary computation, even the universe does not know what the rules are.
No.
And it's trying to figure that out by doing computing.
Yes.
And which means that we know we're not in the no rules one, because otherwise we wouldn't exist. We wouldn't be having this conversation. There's no reality whatsoever. We know we're actually not in the half rules, or rather, it's not that a half rule, but rather it's we know for totality of what the rules are. Only God knows that. Right? We're not God, nor we're the universe or whatever. And then the undecided state is what we're in. It's the game that we're in.
Yeah. Omniscience is God pays no cost to know what the rules are. Sub-omniscience
or he makes the rules.
That's omnipotence. Omnipotence is he makes the rules. Omniscience is he pays nothing to know what the rules are. Omnipotence is he pays nothing to do anything he wants. Omniscience is he pays nothing to find out anything. And
Omniscience essentially means to what's the computation term? Omniscience means that every computation is indistinguishable from a
calculation, or not even a
yeah,
calculation,
like
identity.
every computation you do is computationally reducible versus
Yeah.
non-reducible, right?
Yes.
Which means you can predict with absolute accuracy of all possible outcomes at
Any
zero cost.
context, any yeah, zero cost, any context, any scale.
Right.
Zero cost, infinite, maximal, any cost, or zero cost for any context at any level of scale.
Correct.
And then the human subjects concern what costs we pay at what levels of scale. Like chemistry and physics are not different subjects, but like to do physics experiments, you just need a ball and a stopwatch and an accurate visual like meter of some kind. To do chemistry experiments, you need to like have a galvanometer. You got to measure how much electrical charge is being emitted every time you combine two substances. It's they're not the same cost. You have to pay a much higher price, including dying of metal poisoning, to become a chemist, to just find out what the rules of chemistry are. Whereas for most of the life of a physicist, it's like you sit in an orchard, an apple bonks you on the head, you write some stuff down on a chalkboard, you drop two things off the Leaning Tower of Pisa, you use a pendulum to time them, you see that they fall at the same speed, you make some calculations, and you pretty much know now, oh, we got the rules, it's 1650, how cool, we've got the rules of physics for at least the macro picture. We don't have the micro, we don't have the super macro. But chemistry was like, what the hell was going on in chemistry? They didn't even know atoms existed until like the late 1800s.
Well, I mean, the
It was,
Greeks kind of had an idea.
they had an idea, but it was just like, it was potions. It was just like
Right.
combining potions like a 4-year-old for like 1,000 years, until they got so systematic at the potion combining that they realized, okay, the mass is always conserved. The volume is not necessarily conserved. There are particles probably down at the bottom of all of it that combine in specific ratios. So there's a discrete picture and a conversion ratio between different elements and different reactions. And that's the kind of mathematics that worked out in chemistry, is they eventually discretized all the possible chemical states from one another. And then the the continuous type math got brought in to describe the flow of electrical charge between those atoms. And then there was a thought, maybe modeling the differential equations, which is continuous math, maybe modeling the differential equations of all the different electron clouds, that can help predict future chemical reactions. And to a certain degree it does, but as we're learning, it's even better to just combine everything. You just have to hyper speed up the potion combining at all different pressures, volumes, temperatures, um, densities. Like, we're just going to have to fill in that table of all possible chemical reactions doing it that way. There's no way we can use a continuous theory of temperature, pressure, etc., to account for all the possible state changes. We would never have discovered superfluids like helium when you cool it to 2 degrees Kelvin. It's a liquid that climbs containers. And that boils itself constantly.
Yeah.
Like, or that, metallic gases become Bose-Einstein condensates, where you can run any test on any two atoms and they always return the same four quantum numbers from those tests. And so every atom is behaving like one atom all of a sudden at a Bose-Einstein condensate level. These are just weird things that you don't discover. And I imagine there might even be more. I mean, is the Earth a solid? Not during an earthquake. So there's just so many different in-between states between solid and liquid that to describe it as a continuum is really false. Solid, liquid, and gas are actually just 3 machine learning approximate clusters.
In fact, if anything, the biggest thing I got out of this conversation is when we think of the real world, we tend to think in black and white, solid or liquid, binary terms. Whereas, if we just, as we just found out, reality actually exists in states of undecidedness.
Yeah. So it might be the case that in the chart, the original chart, that games actually has a -2, has several distinct -1 and -2 levels. Just as there are distinct types of games, even at the 0-dimensional, 1-dimensional, 2-dimensional level, there are not distinct types of sets. Sets are just sets. And then when you enrich sets with morphisms or maps between the stone, set is a collection of stones. A category is when you include the stones and the arrows pointing to one another in the stones. And, when those arrows are composable or associative, which they are in a visual diagram. And now the question is, are they in terms of their computation of, if you actually do the algebra? If you can prove that they are, you have a category. But there's only one type of sets, and so therefore there's only one type of category.
Well, so
games, there's many types.
Yeah, I'm looking at the chart, right? So logic, a -1 dimension game, we're talking about, we're saying these are the rules. And the -2 in that empty square right now, it's just whether you have rules or not.
This is a bit of a reach, but I think I have it. I'm going to slide 20. In the case of a -2 game, and so this is, I'm starting with language, and this might fail a Martin or Curt test, but bring it on. We'll learn something. A one-player game, the player plays a 0 game. In other words, he chooses a specific 0-dimensional game.
Yeah, I can play solitaire. I can play Minesweep.
So the idea is that, I think the word plays is not quite right, but the idea is it's like chooses or runs on. So a 0 game, right? A 0 game runs on a logic. So this is a logic, which is really, I was ambiguous about the word logic. It's a set of rules of gameplay.
Yes, it's a set of rules, and it's really a set of algorithms that determine state transition.
And the key is that the -2 category is the live-die distinction. So because the set of rules plays out, in other words, a set of rules is a permutation of the live and die distinction. So a logic runs, a game position runs on a set of rules. A one-player game chooses a bunch of game positions. A two-player game chooses what the one player playing the game positions chooses amongst a set of positions, where another one player is playing a bunch of game positions.
Right, because if I move my knight, it means that you will need to move your queen or whatnot.
And in a game where that knight's there is where that is, yeah.
Correct.
So there's a nesting of that each layer runs on the previous layer. So in the case of game theory, what is a logic? Well, a logic is really a set of rules. And in fact, we might not even be at logic yet. In other words, logic may not be a -1 player game. It might be a -3 player game. It might be that this chart needs to go further than a category, maybe just by one layer. I'm presuming, or maybe 2. Or maybe they line up. Maybe -2 is as deep as you go. But this would be just like living or the idea of persistence itself. So if there is persistence, here's, this is the live-die distinction runs on the concept of persistence. You don't need to have a concept of death for something to not exist. So I know this is very language. This is very word cell, and I know it's
I'm
word cell.
still not so so I'm with you as far as -1 game goes, right? -1 game, we're really just describing the rules. We're describing the functions of state transition.
That's right.
I think -2 is not live or die. I think -2 describes the existence of such rules. The existence or non-existence of such rules. But then you brought up a point that in order for a game to be a game, you have to have live or die condition. So I don't know how that fit in.
There's going to be some way that, just like the Hom set construction from the category theory is like a very technical and tight way of showing how you can generalize down by one dimension until you can no longer generalize. There's going to be some similar, but not necessarily binary logic, but there's going to be some similar relation that allows me to plumb the depths of what are these negative dimensional games. But in general, like I look at I'm already satisfied just with the idea of there being a negative one-dimensional game, in that it's the equivalent of the background in drawings in space. A drawing in space is a game where you do things,
you only have a background, and that it's a thing that it's waiting for an algorithm to start operating, or but that empty space, the equivalence of the rules in games, it's the thing for the game to actually operate on, which is the rules.
That's right. There's like a space in which an algorithm needs to be chosen to implement a game. And then similarly, a one player, even though the one player as an agent isn't necessarily an algorithm, a lot of times in game theory, or when we analyze games, we do it algorithmically. We say, look, honey, if the person hits the tennis ball this way, the best logic dictates that your best option is to go there or go there, right? So if this, then that. Now, in the execution of it, there's all this messiness of whether you can hit the ball or not, or whether your wrist, you get a pulled muscle in your wrist or whatever. But in terms of just game states and transitions, where we don't allow for messy continuous transitions, but instead only allow for discrete transitions between states, right? Essentially, a one player is an algorithm that interrupts the zero-dimensional algorithm or game, and the two player is an algorithm that interrupts the one-dimensional one-player algorithm, which is also trying to play the ball, which is to interrupt the zero-dimensional game. So in tennis, the zero-dimensional game is that the ball's going to go past you and hit the ground. So you have to intercept that. And then the other player now has to do the same thing based on where you've played it. Or in chess, even by accident, your opponent moving could just checkmate your king. So you've got to intercept that. And then you've also, and so forth, and you have a corresponding victory. Chess is complicated, but Go, etc. So it may be the case that what we're really saying is a negative one-player game is waiting for an algorithm to interrupt it. It's a background space, and it's waiting for a set of rules of a game. So then the -2 level would be logic, because the logic would be what is even allowable in the design of a game. What are the final end states of the game, or the final persistent, or what are the allowable states of the game?
I don't know if it's an allowable state in the game.
Constructible states, or
but as soon as you're talking about states,
allowable rules.
Maybe we're allowable rules, probably.
But rules relate to states. Oh, sorry. Go ahead. I'm sorry to cut you off.
Rules. So rules, in my definition, is just a set of state transition. Set of state transition functions.
That's right.
Right. And then if you take it, yeah, actually, maybe you're right. So for a game to be a game, you have to have states. you have to have state transition rules. Those are actually two things, two distinctive things in the set. So then if we then move to -2, then it becomes, well, the question you gotta ask yourself, do you even have transitions? Do you even have states? Do you even have state transitions?
Yeah. This is in the foundational construction of the game. Somehow, what it means to win, what it means to lose. Is it a game? Is it not? Is it not a game?
And I think of, so zero-dimensional game, right? Conway's game of life is the algorithm that just keeps on running. The -1, it's the rules, but your game have not started. You have not even.
-1 is the intro. -1 is the intro screen where it tells you this is what happens when.
No, it's a program, but it's a program before you call execution.
That's right. Before a game state is chosen.
Right. The rules are there. You have not started executing it.
So when rules
in that sense, I think at Big Bang, the universe probably existed in -1 game state. I'm going out on a limb here. In the sense that the rules were already written, but nothing has happened yet. There's no time.
There's no game state on the board. There's no pieces on the board yet. Yeah.
Right. All right.
I like this.
This is fun. We've been going on for 3 hours.
Yeah. I know you got stuff to do too. So we could call it and
let me stop the recording.